To code the microcontroller, we need an IDE. One such is that the Arduino IDU, and this is a sample code that will be injected into the microcontroller. It's a sample code I said. So I have divided this code into 4 segments, and first segment is nothing but the general command. It's according to the coding standards, normal coding standard which we practice while writing the code. We will always start with the command which describes about what the program does all. So here similarly have a command which says that this code has written to switch on the LED for 1 second and then off for 1 second, and then on and off will go off alternatively. That's the ultimate objective, and this knowledge will be injected into the microcontroller with the help of this Arduino. So the second section is that the variable declaration section, in which we can declare the variables. Here variables declared is nothing but int, and since it is outside of any functions, it is a global and it is visible throughout the program. The third section is nothing but the setup section, which will say which pin in Arduino will use as an output pin with described. And the final section is nothing but the loop section, which is nothing but the knowledge or nothing but the logic of the program or logic of the task for which we going to code the microcontroller will be there. Logic will be there essentially in this loop, white loop. Here, since I said that I have to switch off and off the LED alternatively, that logic has been written here, and this has to be compiled, debugged, and run, and it should be thrown into the microcontroller. This is what the overall view how this Arduino IDE will look like. This is the one. For example, see the code will be run on the laptop, and from the laptop through the USB connection port, we will just throw out the logic which is compiled and debug, and that will be thrown into the microcontroller. So we can able to code, program the hardware using this Arduino IDE. So programming hardware can be used to place the program in the microcontroller, and generally it will be stored in the microcontroller memory. The program logic, which will return a code that will be deployed inside the memory of the microcontroller. That is what the essence of this slide. Next component which we're going to discuss. So for now we have been discussing only in the microcontroller. Microcontroller is nothing but the brain of the embedded system. So far we discussed about the microcontroller, IP core, and we discussed FPGA. These are the 3 main components at the center of the embedded architecture. Next, we're going to discuss about the sensor. Sensor is nothing but really which gives an input to the microcontroller. As I said in the beginning of the discussion, sensor is used to take the input from the environment. So it receives input from the environment, and from the environment, it just gives the input to the microcontroller. So we have many different kinds of sensor. One such is that thermistor, which records the temperature of a room, and it will give as an input. And we have another sensor like photoresistor that will report or that will give the intensity of a light. And in the slides, I have given so many sensors, and each and every sensor is being designed for only one specific task. It's only one specific task. So there are about 12 sensors are given here. We'll discuss each sensor and what does it do. We'll discuss in short. For example, a alcohol sensor is used to detect the level of alcohol gas in the air. It will detect the alcohol gas in the air. How much of alcohol gas has been mixed in the air, that will be the output from this alcohol sensor. Next, we have ultrasonic sensor. This ultrasonic sensor objective is to measure the distance of an object. For example, if I have an ultrasonic sensor here, and if I place a pen over here, then the distance of the pen from the ultrasonic will be calculated, and that will be thrown as an output. That is what this ultrasonic sensor will do. Next, we have IR optical sensor. IR optical sensor is infrared optical sensor, which sense the characteristics of the environment around us. Next, we have LDR sensor. This LDR sensor is nothing but LDR, and it's expanded as a light dependent registers, and it detects the light change in the surroundings, how the light changes in the surroundings. Next, we have the gas sensor. The gas sensor detects the presence of the gas in and around us. Next, we have gyroscope sensor, which maintains, which will tell the orientation of an object, whether the object has been placed horizontally or vertically, or it is tilted, the velocity of the object at which it is moving. We want to say if there's a train moving, then I have a gyroscope sensor. It will say the velocity at which the object has been moving, and it will also say the orientation of an object. Each and every sensor will do only a very certain specific task. It will not do apart from what it has been designed for. Next, we have a rain sensor. This is very much used in the irrigation purpose. It will sense whether it has rained or not. It will detect the rain. Accordingly, it will pump the water to the fields. So it is mainly used in the irrigation, and it benefits the farmers. And next we have a sense hat. It will sense the world around us. Next we have photodiode. This photodiode will sense the light detector and convert the light into the voltage. Very important that sense the light and convert the light into the current or the voltage. Next we have infrared proximity sensor, and we have normal that without infrared we have a proximity sensor. These both will use to detect any obstacles in front of. So, for example, this automated car nowadays, Google has brought up the automated car. So, automated car means that the car drive itself without any driver. So, this IR proximity sensor is used in the driverless Google car, where any of the obstacle, if the Google car is driving, if any of the obstacle is in front, this IR proximity sensor will say that this obstacle is there, and accordingly the speed and the brakes will be applied in the automatic car. So it will, this IR proximity and proximity sensor will able to detect if there is any obstacles in front ahead. Next, finally, we're going to see about PR sensor. It is nothing but passive infrared sensor, which measures the infrared radiation from the object. So there are many sensors. I'm not listed all sensors. Some of the main sensor, which is highly important, just mention these sensors. So these are the sensors which is going to give input to the microcontroller, and based on this input, the microcontroller will act upon. And this knowledge in which the microcontroller is going to work will be injected by the programmers or from the users, and output will be given to the external world. And that will be done by the actuators. Next, we're going to see about the actuators. So the actuators are the one that will take an input from the microcontroller and will share that input to the outside world. There are nearly four type of there are nearly four types of actuators, and I have given them as a figure: linear actuators, motor actuators, relays, and solenoids. So linear actuator, what they actually do is that they are used to enable motion of an object in a straight line. And the motors, they enable the rotation movement of the device components or the whole object. And the relays, this category includes electromagnet-based actuators to operate power switches in the lamp, heaters, and even smart vehicles. So on and off, this had to be done with relays. And solenoids, and this has been mostly used in the home appliances as part of locking and triggering mechanism. So if triggering mechanism mainly works in the home appliance, because if these conditions occur, then this has to take place. So certain action has to take place only if the condition has been met. So for this purpose and all, we use solenoids. For example, if there is a if there is a gas leakage, then we have to raise an alarm. So when there is a triggering mechanism is required, the solenoid actuators is being used. As the sensor, there are different types. We have different types of actuator also. So I have tabulated some of the actuators and what action we can expect out of the actuator. The first actuator is that LED bulb, and of course we can get the light from it. Next we have heater actuator, which increases the temperature. Next we have a cooler actuator, which will cools the temperature or reduce the temperature in the room. Next we have motor actuator, which will spins or rotate around. Next we have a pump actuator, which will pump the water or air through the pipes. Last we have a buzzer, bell, and siren actuator, which will create noise based on the inputs, which is output, which is received from the microcontroller. So for now, we have seen we had an elaborate discussion on components of embedded system. First, we had seen about sensors, and the main important part, the core part of the embedded system is nothing but a microcontroller. We have an extensive discussion on the components of microcontroller like IP code, FPGA, and the microcontroller. And the last component of the embedded architecture is actuators. We have discussed in detail about this, all these things. And one more component in the architecture, embedded architecture, which is there, is nothing but analog to digital conversion. As I said, this analog to digital conversion plays a crucial role to give an input to the microcontroller. So I will see how it plays a crucial role in giving an input to the microcontroller. Any real world, the signals we can classify as an analog signal. And this microcontrollers will work only on digital signals. But the microcontroller will take input from the real world. Real world through sensors. The sensors will give an input from the real world to the microcontroller, but the sensors detect the analog signal. So this analog signal will not be understood by the microcontroller. Somehow we have to convert the analog signal detected from the real world to the digital signal so that the microcontroller can act upon the digital signal. So somehow we have to convert the signal analog to the digital. So we have analog to digital conversion. If you want to map this analog, we can map this analog to integers. If you take a numbers, we can map this analog to integers, and digital signal we can map to the real numbers. Why we can map this analog to integers? We can say is that, for example, in the range 0 to 1, can you say how many number of integers are there? So for now, we have seen the three main components of embedded system architecture. The first is sensor, and we have seen extensively on microcontroller, IP and FPGA, and we have also seen on actuators. If we keenly look at the architecture that has been given at the bottom of the slide, there are two other components which we need to discuss, nothing but ADC, nothing but analog to digital conversion. Another component which we are here to discuss it, DAC, this digital to analog conversion. First, we'll see what is analog and why we need to do this analog to digital conversion. As I said, any input to the microcontroller will be given by the sensors, and then sensors will take the input from the real world. You all know that the real world signals, real world signals are analog, and these analog signals will not directly be able to processed by the microcontroller, and because microcontroller digital, so this somehow these analog signal has to be need to be converted into digital, and this conversion will be taken place by ADC conversion, like analog to digital conversion. uh, for easy understanding, we can say this analog system, analog signal can be easily mapped to the real numbers. Real numbers are infinite for any given range of numbers. For example, it takes 0 to 1, and if we ask how many number of real numbers are there in the range 0 to 1, there are infinite number of numbers. We can say from 0 to 1, we can say it's 0.5, 0.6, we can say 0.555, we can say similarly 0.56. Infinite number of real numbers that is present in between the given numbers, and we can map this the digital signal to integer numbers. If we say if we ask a question that how many integers are present in between the range 0 and 1, there are only two integers. One is nothing but 0, another is nothing but 1. It can be mapped to that. The integers can be directly mapped to the digital signals. So somehow we need to convert these analog signals from the real world to digital signals so that it can be easily processed by the microcontroller. For example, if we take from the real world, I sense if we have a sound, if you have a volume system speaker, and the speaker will throw a sound, and the sound can vary from low to the maximum, any range. If we fix the range like 0 and max, the speaker can take any of the values. It can take 0.1, 0.2, or 1, 1.1, 2.1. It can range any number of values within the given range. And if we have a light, and if we have a regulator for adjusting the dimness of a light, again that can be mapped with the analog signal. In general, real world will get only the analog signal, and for digital, if you want to give me an example, we can say digital watch, in which we can get the minutes or the seconds, and we will not get the fraction of second in the digital watch. So we can map that for the digital signal, digital watch for the digital signal. So somehow this signal, analog signal from the real world will be converted into digital signal so that the digital signal can be able to process by the microcontroller. So we need this ADC. Similarly, we have digital to analog conversion. So once the microcontroller receives that digital signal from the analog to digital converter, the digital signal will be processed by the microcontroller and the output will be in the form of digital. But you know, the real world signals are analog and the digital signal need to be converted into analog so that it can be passed to the real world. So again, we need one more conversion at the actuator side. At the output side, we need one more conversion that will convert the digital signal from the microcontroller to the analog signal for the real world. Suppose, as I said, again, actuators, we have discussed a list of actuator. One such actuator is nothing but output, and is nothing but a speaker. So the digital signal which is out of the microcontroller will have to pass to this DAC, which will convert the digital to analog, and we can be able to hear the sound. This is how the digital to analog conversion works in the embedded architecture. So now with this slide, we have come to the end of discussion of all the components inside the embedded system architecture. Most of the chips are embedded systems, and slowly the manufacturer and the user are trying to incorporate this network component in it so that these embedded systems are trying to become slowly an IoT device. Because so we have intelligent because the microcontroller has intelligent because the intelligent can be put into the microcontroller using the Arduino IDE, which you have seen just few slides back. The intelligent component is there. The only component which is missing in the embedded system is running by the internet. If you add this network to this embedded system, it will become an IoT device. Next, we're going to see the various platforms and tools to build the IoT projects. So, an IoT platform and tools offer many services that ease the way, ease the job of the programmers to inject the logic into the microcontrollers. So IoT platform and tools are considered as the most significant one for the IoT ecosystem because unless otherwise these IoT platforms are there, it will be very difficult for the programmers to code and put the logic inside the microcontroller. So this facilitate or this makes the job of the programmer much easier way. So there are many platforms. We're going to discuss around 12 different platforms, and we're going to take top 2 platforms, and we're going to see which platform is good for which application. That is what the presentation is tuned for the next 20 minutes. The first is the Zeta platform. It is built on Node.js. It's an API-based IoT platform, and it is based on Node.js. It combines the REST APIs, web sockets, to make the data intensive and make this a platform suitable for the real time. These APIs are playing a very crucial role. Next, we have Arduino, the sample thing we have seen in few slides back. So it offers a appropriate blend of IoT hardware and software, and it's a very simple IoT platform. Third, we're going to see Node-RED. Again, like Zeta, this Node-RED is also built on Node.js. It provides developer to connect devices, services, and any number of APIs can also be incorporated. And it also provides the browser facility for the Flow editor. Next, we have Flutter platform. It's a programmable processor core for electronic project. This Arduino-based boards includes the wireless transmitter. This means the Flutter board includes the wireless transmitter. So Wi-Fi has been enabled in the Flutter that can show the signals nearly for an half a mile. This Wi-Fi signal from the Flutter will be sensed, can be ranged, covered. Next, we have a platform MTM Lab Mainspring. This is an application framework which is mainly developed for machine-to-machine application like remote control, flight administration, and smart terminal. This platform has been mainly used. Next, we have Things Board platform. So this is used for collecting the data from the sensors, processing, and how this data collector will be visualized. As all things can be done at ease with this Things Board platform. Next, we have Kinoma. Again, this platform is mainly designed for semiconducting hardware prototyping platform, and it connects freely with iOS and Android app. Next is Ka IoT platform. This car is a production-ready, flexible, multi-purpose middleware platform for developing end-to-end IoT solutions. Next, ninth platform we're going to see is Siteware. This platform offers injection, repository, processing, and assimilation of different input units to the IoT platform. And this Siteware run on Apache Tomcat, and it also enable us to connect this IoT to the MongoDB databases. Next, we're going to see DSA platform. DSA stands for Distributed Service Architecture. And this platform is mainly used when we have this IoT infrastructure distributed at various locations. And it's something very upcoming, and it has been used for distribution IoT application. This has been extensively used. Next, we have prominent platform is Thinker.io. It's a scalable, it's mainly provide a scalable cloud for connecting devices. We'll see extensively how this cloud, IoT, analytics are all related in the next webinar. And this Thinker.io will always provide scalable cloud services for the IoT devices. It also supports the Raspberry, Intel Edition, and other platforms. Next, we have a Raspberry Pi, which is very, very cheap. And it's a mini computer that even can run the Linux OS. It also provide general purpose input output pins that allow you to control the electronic component. So these are some of the components, platforms, and tools which is available for the IoT, Internet of Things. Among this platform, the most used are Arduino and the Raspberry Pi. So we're going to take and we're going to have a deliberate discussions, detailed discussions on these two platforms. So at the bottom of the slide, there are two pictures. One is Arduino, and the other one on the right-hand side is nothing but Raspberry Pi, and the left-hand side, you can see a figure, and it's nothing but, I'm talking on my left and on my right. So on my right is the Raspberry Pi, on my left is the Arduino. Generally, IoT programmers and IoT experts know for what kind of project they need to use Arduino, and for what kind of project they need to use the Raspberry Pi. But for the beginners and for the students who are venturing into this IoT, they will be really confused. So I have a couple of slides for you to know when to use what platforms for developing the IoT projects. Before that, we need to know what is Raspberry Pi. So we'll have some discussion on Raspberry Pi. Raspberry Pi is a board, and we can call it as a fully functional computer or a full-fledged computer. This Raspberry Pi has a dedicated memory, it has a dedicated processor, and it has also a graphics card. This Raspberry Pi runs a very specially designed Linux operating system, and it is very easy to install because it runs on the Linux operating system. It is very easy to install any of the Linux software, and it establishes some sort of comfortness in the Linux operating system. And this Raspberry Pi is mainly used for video game emulator. As I said, since it has a graphics card, when you want to test the functioning of a video game, this will be used as an emulator. The Raspberry Pi doesn't offer much internal storage, but you can always use the memory card for the memory, which will allow you to store a quite reasonable amount of program size. So generally, Raspberry Pi is 512 MB RAM, and it will be 700 megahertz microprocessor, and hardware supports SPI, I2C, and it is serial. This is one of the pros of using the Raspberry Pi. So if you use the Raspberry Pi, it will be easy for us to connect with the network. And as I said, it will be Raspberry Pi will be much comfortable with the Linux software and operating system. And this Raspberry Pi can be programmed with any languages, including Python. Some of the disadvantages of Raspberry Pi is that accessibility to the hardware is not of real time. And if the CPU is busy, microcontroller is busy, then the interfaces with the hardware will be quite delayed. So for the real-time application, I think if you want to access the hardware, I think this Raspberry Pi is not that great. And it does not have enough power to drive loads. And there is no inbuilt analog to digital converter available. If you want to use that, then you have to separately install it. And the hardware design of the Raspberry Pi is not an open source. Uh, so that's also a big disadvantage of the Raspberry Pi. Next, we're going to see when you should use, for what kind of IoT project we're going to use the Raspberry Pi and when not to use. It's a very, very crucial point. So if your IoT project has very limited number of interaction with the hardware, then the Raspberry Pi is the best opted platform for you to develop the project. The interaction with the hardware should be very minimal if you want to use the Raspberry Pi. And if your project also falls in this line, then the best one is the Raspberry Pi. And when your IoT project needs an internet, then it's a good choice. And if you want to use variety of programming languages, you want to code with variety of programming languages, then again the Raspberry Pi is an apt one for you. When you don't want to use, when see, we have seen what are the applications we can use a Raspberry Pi. Similarly, we should know or what kind of IoT projects we will not use a Raspberry Pi. If your project requires a lot of hardware instruction, then Raspberry Pi is not for you. So for the past 5 minutes, we have been discussing on Raspberry Pi. We discussed what is Raspberry Pi and what are the pros and cons of Raspberry Pi, when to use Raspberry Pi and when not to use the Raspberry Pi. Next, we're going to see what is an Arduino platform. Arduino platform is composed of mainly three components. They are hardware prototype platform, Arduino language, and IDE, Arduino libraries. Few slides back, while discussing about the microcontroller programmable, you have seen a screenshot of my Android Arduino IDE. And this Arduino boards also contains the microcontroller, and it is not a full-fledged computer like the Raspberry Pi. And like Raspberry Pi have a lightweight Linux operating system. Here, this Arduino does not run on the full operating system, but simply you can write the code and execute as the firmware interrupts it. The pros and cons of Arduino. Advantages is that we can easily start with Arduino, even if you don't know, if we are a very beginner in IoT, you can easily start with Arduino because it's very simple. It's for beginners. So you can easily get comfortable and accommodated with this Arduino. And it is really used for the real-time applications because both the hardware and the software is of open source, and IDE is also open source. And you need not to have a very good programming knowledge to code with Arduino. That's a very big advantage. As I said, it is useful for beginners. It is very easy to extend and has the user contributor shields and libraries. There are many number of libraries present, so you can use the library whenever you want for a very standard task. The disadvantage mainly with this Arduino platform is that it is not powerful as Raspberry Pi. And if you want to code in Arduino, you have to code only with C and C++. You have to have some sort of knowledge on C and C++. You cannot use Python in Arduino. It will only work on C and C++. And third main disadvantage is that connecting to internet is difficult. It's possible, but it's difficult. Next, you're going to see when we can use Arduino, for what kind of project we can use this Arduino. If your project requires you to have a lot of interaction with the hardware component, then Arduino is the right choice. But when not use this Arduino is that if your project requires to have a complex software which has been coded in many other languages, then this Arduino platform is not a right choice, then you have to go with the Raspberry Pi. So for the past few minutes, we have been going through on the different platforms. We discussed Arduino, and then now we are discussing on Raspberry Pi. Also, we discussed. Now we're going to compare Raspberry Pi and Arduino on 6 different features. The features are programming language, processor speed, internet connectivity, hardware design, real-time whether it is suitable, and analog to digital conversion. So if you take the feature programming language, we can code the Raspberry Pi with the many programming languages, whereas in Arduino, you have to use only C and C++. And processor speed of Raspberry Pi is 700 megahertz, and Arduino it is 16 megahertz. So it is much higher. The processor speed is much higher in Raspberry Pi. Internet connectivity in Raspberry Pi is very easy, and Arduino it is possible, but we have to work a lot. Next, hardware design for the Raspberry Pi is closed. It is not open source, whereas in Arduino, it is an open source. Real-time application hardware, it's not real-time in Raspberry Pi, whereas in Arduino, it's a real-time. And analog to digital conversion part is not there in Raspberry Pi, but we have the same in Arduino. This is a quick comparison of Raspberry Pi and Arduino. That's the end of the today's session. And before we wind off, I'd like to have a summary on the discussion which we had today. Today, topic of webinar is on IoT architecture. Before we get into the architecture, we had a short discussion on embedded system, how it is different from the real-time system, what are the constraints by which this embedded system is functioning, and we have also seen this embedded system architecture and characteristic. And in the architecture, it mainly has the three components. One is sensor, and middle part is nothing but brain, which is nothing but microcontroller. Third part is nothing but actuators. And we have a subcomponents, nothing but analog to digital conversion, which is there between the sensor and the microcontroller. And another small component we have is digital to analog converter, which is between the microcontroller and the actuators. We have seen each of the component in discussion in detail, and we have also seen how we can able to code the microcontroller and what are the different platforms and tools which are available to code this microcontroller. We have discussed around 12 different platforms, and among the 12 different platforms, we have chosen the top 2 platforms that have been used frequently by the programmers in IoT. And among that, we have chosen Raspberry Pi and Arduino, and we have a detailed discussion on pros and cons of Arduino and Raspberry Pi, and when we should use the Raspberry Pi, or what kind of project we should use the Raspberry Pi, and for what kind of project we have to use this Arduino, and when not to use both Raspberry Pi and Arduino. We have discussed in detail, and we also compare this Raspberry Pi and Arduino on 6 different features. And that's the end of second webinar. And day 3, we're going to discuss on IoT, analytics, cloud, and edge computing. So these are the references that I have referred to prepare this presentation. And thank you so much for your passion listening. And if you have any doubt, you can reach me at tiago@cutn.ac.in. Thank you so much.